Okay, so our next session would be two state-of-the-art solution. This presentation on this 3D occupancy predictions. So two very exciting presentations. So the first one is from Chonghao Sima from Shanghai lab. So this talk will be online. And the second is from Zhiding from Nvidia. So this will be in person, right? So let's welcome Chonghao Sima first. It will be an online talk. 20-minute online talk. Yeah.
Okay, so thank you, Ziwei, for introducing me. So hi, everyone. My name is Chonghao Sima. I'm from the OpenDrive Lab at Shanghai Lab. So today I would like to talk about, from bird eye view perception to CNS occupancy, an overview of camera 3D perception done by OpenDrive Lab in recent years. So let's give us some background knowledge about why we need 3D perception. So apparently we have 3D perception in terms of driving to sense the world around, and then in the robotics and embodied AI, we also need the 3D perception to find the affordance in the surrounding environment to get what you can touch or to do the housework. And so why we focus on camera-based methods? So there are some basic reasons for that. So it is low cost. It is easy to deploy. It can sense long range, and also it is rich in semantic appearance. And so what is the core issue in camera-only 3D perception? So we think that it is the accurate depth. So this is a bridge. So if we fill with the accurate depth, so we can bridge the gap between the camera-based and the LiDAR-based method. So here is a simple example to help you to understand this. So in the monocular 3D detection or tracking by detection, if we have a depth arrow, you can see here in the BV bird eye view. So you can see that depth arrow will cause the big gap between the ground truth and the prediction bounding box. But we fill with the correct depth or at the same time, so the ground truth and the prediction will align well. And then how do we solve these accurate depth issues? So there are many tracks to solve this. One is called the pseudo LiDAR. So we can predict. So if we don't have the accurate depth, we can predict the depths to form such a pseudo LiDAR things. And then is the center point track. Here we can detect the heat map in 2D to infer the pose in 3D based on the geometric mappings from the 3D space to the 2D perspective view. So the first way is to do the depth pre-training. So we can embed the 3D prior knowledge in the 2D pre-trained backbone, such as the work done by the TRI, the DD3D works. So it is a very successful 3D backbone used in many challenges and many 3D works. So the last thing is that we can do the bird eye view transformation. So we are transforming the perspective view feature to BV feature to facilitate the following task. So there's a trending in the bird eye view perception in recent years. So from 2021, we have HD MapNet, which is given the HD map in the bird eye view coordinate to propose the aggregation feature based on both camera and LiDAR. And then later years, we have the DTR3D and the BVDAT. We are able to fuse the object detection using the omnidirectional cameras in BV. And then in 2022, we have the BV transformer to explicitly construct the BV representation feature from the camera parameters. And then later we have some fusion works, so sensor fusion works such as the BV fusion at the FQ TR3D. In this time, we are fusing the multimodality features in the bird eye view representation, since it is a very convenient way to fuse the different modalities features. So the core problem here is that how to model the view transformation from the perspective view to bird eye view more effectively. This is the core issue when we do the bird eye view perception in camera-based methods. And then let's go into a deep dive into the view transformation. So there's basically two ways to do the do the transformation. One is from the 3D space go back into the 2D space. So this is basically a camera projection figure to help you understand that if we have a 3D, if we have a point in 3D space, how to project it back to the camera plane. So by doing this, there's a problem that multiple 3D points will hit the same 2D pixels when even when the resolution is very low. And then we can also have another way to do that is that we are given the 2D image, we can predict the depths per pixels to reconstruct the 3D space. So so this is another problem is that the depth is unknown for each pixels. So it is obvious that both way has its pros and cons. So so no matter what, the view transformation itself is a ill-posed problem. So to address these issues, there are basically two ways to address the view transformation. One is based on the 2D to 3D prior. So now that the depth is unknown, we can predict the depth itself. So this work is illustrated by the famous work like the leaf splash shoot and its variant like BV depth, BV depth, all this work. And another line of work is the pseudo LiDAR family. So the second way is that we based on the 3D to 2D prior is that we index local feature according to the projection from the 3D to 2D. So one promising work is shown by the DETR3D and its variant. And then the second work is done by some explicit BV feature construction, such as BV former, which I will introduce later. So the third way is an implicit 3D positional embedding, which we can embed the 3D position back into the 2D coordinate space. So now let me introduce our work in CVPR23, the BV former. So the setting is that we are given multi-camera and the temporal input. We can construct a BV feature based on this multi-camera and temporal feature by using the deformable attention, and then we use a BV query to look up for a current BV feature map. So here the BV query has two attention mechanism to do the fusing. So first is the spatial cross attention mechanism. This is to fuse the multiple camera feature into the same BV grid space. And the second is the temporal self-attention. So this is to aggregate the temporal feature from the history. So this figure illustrates the idea very well. So now we start from the BV query. We have an ego card here, and now we want to know that what is in here at time step t. So we go two ways here. The first way is to do the temporal self-attention. We go back to the history BV feature and check that what was in that grid in the time step t-1. And then the second way is that we do the spatial cross perspective view on the image, and then we sample the feature back into the BV space. So this is a multi-camera images at time step t. So that by fusing these two features, we can construct we think is a very strong and very expressive the BV feature at time step t. And here is the BV former pipeline. So for more detail, you can check out our GitHub repo. Yeah. So here is also a visualization result of the BV former on the new set dataset. And then we have a second work called the Transformer. This work is from a similar idea, but we are focusing on the 3D link line detection task. So we are instead of using the sampling task, we use the IPM-based cross attention for BV feature. The IPM here means the inverse perspective mapping. So we sample some 3D points based on the assumption that the ground is flat, and then we sample some point in the 3D space and back project them into the 2D space. So both the BV former and transformer shows that the BV perception is prevailing since the 2022 in academia. And then we want to ask a question in the next step, say, what's its problem of current 3D perception representation? Say bounding box is a very prevailing representation. So bounding box, 3D bounding box itself, it ignores the detailed geometry of an irregular object. Say that you have a irregular car here, you have the arm out of the bounding box, but your bounding box cannot just depict the arms very well. So if instead, if we use the 3D occupancy here, it can catches the geometry shapes well. And also the mobile eye and Tesla also adore such a representation, as Feldon just said that. Yeah. And so so back to here, I would like to go over how does the 3D perception evolve into the 3D occupancy? So back in 20,000, we have Professor Andrew Zisman to write a book about the multi-view geometry in 3D computer vision. It basically tells us how to do the 3D geometry mappings and projection between the 2D and 3D space. And then in 2012, we have a Kitty dataset release. So this sets the benchmark for the monocular, stereo, and LiDAR 3D object detection. So after that, 3D bounding box become the prevailing representation and all the task objectives for almost every 3D vision task. So we have many baseline methods at that time to be established, and then those methods you know well. So I won't read them one by one. So meanwhile, at the same time, we have the NewSense dataset and the semantic kitty released. So this introduced two new works, two new tasks here in 3D visions. One is the multi-view 3D object detection and the map segmentation. And then also it introduced the LiDAR segmentation and the semantic scene completion. And we noted that the semantic scene completion is very close to the idea of 3D occupancy, although it, in the scene completion task, it emphasized the need of completing the scene based on the LiDAR input. So instead, we are starting a camera-only methods to complete the 3D scenes. And then later, the people in academia and industrial start to address the monocular and LiDAR and fusion tasks. And at that time, many industrial preferred methods were proposed, like the center point, like the FCOT 3Ds. So at this time, the 3D vision tasks are getting advancing. And then at that, meanwhile, we have the panoptic NewSense release. It is a LiDAR panoptic segmentation and tracking task, so that it provides the foundation of doing 3D occupancy in later years. And after the 2021, so the academics starts to shift attention to address the BV map and lane detection and segmentation. So these I would say these are the static objects on the road instead of the dynamic objects like cars, trunks, and the pedestrian. So meanwhile, at the dataset side, we have the Waymo open dataset and the open lane release, which is a larger scale LiDAR and camera 3D object detection for the academy. Yeah, so since 2022, so the BV perception is prevailing. So many multi-view and temporal clues or priors are addressed by these methods. And later in this year, we can come to a great attention on the occupancy tracks. So in occupancy, we would like to I would like to introduce our challenge this year, host with the Tsinghua Mars Lab and the Motional, and we have done a very great job in this. Yeah. So let me introduce the 3D occupancy prediction challenge. So in this task, the input is the multi-view images, and we output the occupancy state and the semantics labels in the 3D scenes. So yes, you can see the visualization here. This is based on the NewSense dataset. So what is interesting here? So the first thing is that we have the camera only. It is a camera only general scene perception, and the second is that we are working with Motional to exclusive generate the test set labels. So based on the challenge participation, we have see some trends in the 3D occupancy. The first is that the BV perception, the idea of BV perception is still prevailing. Many methods start to reconstruct the 3D occupancy based on the BV perception, BV features or perception results. And the second is that we found that the depth supervision matters in many very good participants methods. And then we found that the data augmentation and 2D supervision also helps the 3D occupancy. And then we have some interesting finding that the occupancy is better in depicting the geometry of the scenes, while the 3D bounding box is better in object class prediction. And then we found that for the network itself, so the bigger backbone, the better performance. This law is still exists. So the benchmark, we introduce some dataset stats and the visualization results here. So if you're familiar with the new set dataset, it is almost the same. So for the metrics, this is a tricky part for, since it is the first time we host the 3D occupancy challenge. We use a very simple matrix called the mean IO view, which you are very familiar with the semantic segmentation task. And then I think that for the matrix part, it would be much more advancing or much more attracting that we can devise more metrics based on the need of the 3D occupancy. So here I post a QR code here for you to scan it if you want to learn more about these tracks. And there's some challenge stats here. So it shows that this is the most fierce contest challenge this year. So we have participants ranging from the academy to the industrial. So we have 145 teams participating, and the country regions are covering 10 countries and regions. And we have more than 400 valid submissions. So the SOTA performance double from the baseline. So we have the baseline methods released at 23.7 at MIOU. So finally, the SOTA methods reached 54.19, yeah. And the matrix variance, the top three matrix variance is only 1.4. So it shows that the contest is very fiercely. So here is the challenge leaderboard. So the top 10 elegance here. So we have the Nvidia team as the outstanding champion. The 42 dot from the South Korean have the run out. So we also have an innovation award to the fifth place, the Harbin Institute of Technology. They are performing very insightful how to do the 3D occupancy from academic, so you can better check them papers. So all of these leaderboards and their papers can be accessed by our challenge website here. So I place a QR code here for you to visit. Okay, so it's about 20 minutes, so I think I should switch to the Nvidia team for them to give their presentation of their methods. So yeah, thank you.
Research scientist at the Machine Learning Research Group, Nvidia Research. So before joining Nvidia in 2018, he obtained a PhD in ECE from Carnegie Mellon University. So he is the outstanding champion of the 3D occupancy prediction challenge. So Zhiding's talk title is 3D occupancy prediction based on forward backward view transformation. So let's welcome Zhiding.
Yes. Oh, okay. Okay. Hello, everyone. Thanks for attending the talk. Today I will present the FBOCC 3D occupancy prediction based on forward-backward view transformation. This is a winning solution for the 3D occupancy prediction challenge. This work is jointly done with Zhiqi, David, Mingxue, Shiyi, Yang, and Jose. So recently, 3D occupancy prediction emerged as an important task for AV. And compared to object detection, 3D occupancy prediction incorporates more richer real world information. And therefore, these information are very important towards the planning and prediction stack, and therefore towards end-to-end driving. So if you look at some of the, in the academia, people have been thinking about like similar problems, for example, semantic scene completion, which is in some sense also this semantic occupancy prediction. And there have been solutions based on various modalities. So for example, we have these, we have LiDAR-based solution. We have solutions based on RGBD camera where you have the additional depth modality. And then, of course, there are works that start to address camera-based occupancy prediction. And obviously, camera-based occupancy prediction is very challenging because you only get 2D input, but you have to output the 3D without any depth information. You actually have to infer from the camera. But the good thing of camera-based solutions, of course, cameras are very convenient to gather the data and also cheap to use. So this is the advantage. So and when we think about these 3D occupancy prediction, they are also highly correlated with the traditional 3D object detection. In the sense, we talk about perception in the BEV space. The difference is mostly we are encouraging denser and richer output from the network. So therefore, the network designs of 3D occupancy prediction are very naturally highly correlated with existing BEV perception solutions. So that's why I'm going to give some brief here, because there are many BEV solution state-of-the-art work. So I'm only picking two that are closely related to what the solution we built on. So the first one is BEV depth. Actually, this one is an example of constructing the BEV features using forward projection. The forward projection method they use is a lift splash shoot, which is also a method proposed by Nvidia, by Science team. So the way this works is that you could leave the you use an image encoder to encode the image features, And then what they do is that after lifting, so they use the LiDAR depth as a depth supervision to actually supervise a depth network built on top of the image features. And this depth supervision turns out to be very, very important for the accuracy of the BEV perception. And you can incorporate this depth information together with the context feature, and you build up the BEV feature. This BEV feature now has a good sense of the depth perception. And finally, you try to output the bounding box inside the BEV space. And note that this work is actually heavily based on Seong-Gyun's, but the next work that I think just now it was introduced is a BEV former. This is also the work done by Zhiqi. And other authors from Shanghai Air Lab, and also so this one is actually a transformer-based solution for BEV, and this one actually features backward projection. When we are talking about backward projection, we are talking about we can build up learnable queries, learnable transformer queries in the BEV space, and back projecting to the 2D camera domain using deformable attention. So from this, we talk about these two works mostly because they are very representative works of forward projection and backward projection. These are two kinds of projections that are predominantly used nowadays in the state-of-the-art BEV solutions. And also there are some interesting works that are directly related to this occupancy prediction. And if you look at their architecture design, it's also highly related to this BEV solution. So for example, this monosync is one of the very early works that start to address camera-based semantic sync completion using neural network. And if you look at, and basically this module here is also a 2D to 3D view transformation module, very similar to orthogonal feature transform, but in a multi-scale manner. And then they have some UNetch module that after you basically aggregate these features in the BEV space, you can use a UNet architecture to process it in the BEV space and finally output these predictions. The other work, which also we proposed this work at Nvidia, is Voxformer, and actually this work is accepted to CVPR this year. So we will also present this work at CVPR, and this one features a two-stage framework with backward projection. It's kind of similar to BEV former, and the way that it works is that it has two stages. In the first stage, you actually have a depth network that kind of propose a set of sparse queries in the space. The logic and the intuition behind this is these visible queries in the 2D domain. They are the most they contain the most abundant feature. They are the most reliable ones. So that is why you start to fill in the missing information, starting by prioritizing the featureization of these sparse queries are important because they are the most reliable one. Then you start to fill in and use an MAE styled approach in the second stage to fill up the missing pieces in the BEV space, and finally you have a dense output to predict to give you the occupancy prediction. But one of the maybe small limitation is that this is a two-stage, and then it's not a single architecture. And also I will soon also talk about the limitations with forward and backward projection together. So here's the proposed model design. So if you think about this is a typical architecture of a camera-based BEV perception solution for autonomous vehicle. So you have multiple camera input, you have image encoder that encodes these camera input, and and then there is a module that is 2D to 3D view transformation module that leave these 2D image features into a BEV, into a Minecraft world space, centered at the ego vehicle. And then you have some encoder decoder in the BEV space, and finally you do the prediction. Now this view transformation, no matter forward projection or backward projection, it's very important. It's at the core of these BEV perception and pros and cons with forward projection and back projection. So when we think about forward projection, the good thing is we start from camera pixels, and we build up we project the features into the BEV space. So a resulting problem is that because you are shooting rays to the BEV, that's why the rays gets more and more gets sparser and sparser as they go away from the from the ego vehicle. So that is a problem, because ultimately your prediction are based on these BEV features, and if the rays get sparse, that means the sampling at those locations gets sparse, and that creates some problems for the prediction. This is one thing. But the good thing about these is, for example, method like lift splash shoot, they can encode the depth prior information very well. So using depth pre-training techniques works very well for this forward projection method. The other way around is a backward projection. And the backward projection, the representative work, of course, is a BEV former. But the problem is, as you start from a query and back project into the camera domain, you don't have a sense of these depths. So that is why actually you start to see these very like ray-like heat map, these emerging in the BEV features, and that causes a problem. So when you have an object and you tend to get false positives, multiple duplicate detections along this ray due to these undesired activation heat map along the ray. So is there a way that we can combine both? And this is our forward-backward design solution. So basically, what we have is that we can use LSS like lift splash shoot, like forward projection, to create a feature, to lift the feature into the 3D space while using depth to supervise that. We can collapse those features into a BEV 2D flattened BEV feature and use them as to initialize the learnable queries in the BEV space and back project the queries back to the image feature. So this backward projection part is very similar to BEV former, is using deformable attention and then we can also find a way to combine these voxel representation from the forward projection and also these BEV feature from the backward projection, fuse them together, and then go through an occupancy head to predict the final occupancy. So you can think of this architecture at high level is organic composition of BEV depths and also the BEV former, and finally in the BEV in the BEV space, once you have these fused occupancy, one of the things we do is that we can reduce the resolution at multiple scales to increase the receptive field, and then expand back, and also then finally supervised by the occupancy ground truth. This is the head design. For more details, please refer to the report. So there are, of course, we are since we are participating in the challenge. So besides the model design, there are many things that are important for achieving state-of-the-art performance. So here I'm going to introduce this bag of tricks. Talking about scaling up, we use the in turn image H, which contains 1B parameters as the encoder for the image encoder. Turns out this scaling up law applies very well also in the 3D occupancy prediction. But the problem is that once you have 1B parameters, when you apply the training on the new thing, it's very small. The data set contains very little samples. So it's basically an in-domain data. It's not very suitable for large-scale pre-training. So when you do the pre-training, you want to do it on maybe very generalized like web data with a lot of diversities. So that is why we deploy this pipeline where we start from ImageNet 22K pre-training, and then we next go to 2D detection. We basically train the network using the 2D detection head on object 365. Then we do in-domain pre-training. This in-domain pre-training are depth and semantic segmentation prediction. So for this part, actually, it's interesting. We use the latest work from Segment Anything. We use Segment Anything as an auto-labeling tool to treat the bounding boxes and also the point cloud as prompts, and use that to auto-label the new things images. So once you got the segmentation, you can actually use these segmentation as a very strong supervision signal to prevent the overfitting, and together with the depth map here to do to supervise the backbone as this is shown on the right. And of course, post-processing, I think this part is a little bit less interesting, but since this is a challenge, this is needed. So we have we used temporal test time augmentation. Basically, you have different kinds of perturbation flips, and you ensemble the method, and also temporal TTA, where we consider different frames and aggregate the information along the temporal, and this will refine your final result. The other is ensemble. When we ensemble, we have ensemble from different models. And when we are doing the ensemble, we consider the weight from different categories and different models. For the weights from different categories, they are determined by the IOU of the output from different from the different classes. This is not hand picked. This is actually is determined by the method. The model is validated. The weight of the model is actually searched on the validation set. Okay, so here are the experiment results. So we using these using the bag of tricks and also the model design, we were able to push from the very basic 23% IOU all the way to 42. All these are controlled experiment on a ResNet 50 backbone. And we can see from the curve that several things matters. Depth matters, and actually visible mask matters for a lot for training. So when you are doing the training, don't try to use garbage information, only use information from the visible part. And this is also quite a coincidence with the philosophy of Vox-Former, start from the visible part. And also temporal also seem to help a lot here. So these are the other findings. And we also did some experiment trying to scale up the models. And finally, our largest model with more than 1B parameters pushed the performance to over 52% MIOU. And we also did some study, like studying these BEV representation. We find that both the BEV and the voxel representation, they together benefit each other and give some performance improvement. And this is the final result. So after using model ensemble and also using all the bag of tricks, we are able to get 54.19% MIOU on the leaderboard, which ranks first among all the submissions. Here are some comparisons between FB OCC, our final solution, compared with the baseline starting from BEV-DAT. You can see that on some irregular shaped objects, the prediction gets better. And also we notice some noise in the data set itself, hopefully can provide a useful case study. So the inconsistency between the camera mask and also this GT versus our final prediction, you could see that the prediction here does a pretty reasonable job, but the evaluated MILU on this one is quite low. So I think there are some inherent noise in the data set as well. And here's a video showing these, I think this will be the last one. It's showing the prediction result. I think still, even though the numbers looks high, but I think there are still pretty much space. I would say this challenge, camera-based occupancy prediction, is a very challenging task, and it has a lot more room to improve. So that's my take from this. We will release also open source the code at the following repo. Thank you all for attending the talk.
Okay, so let's thank Zhiding and also congrats to Zhiding for leading the lecture. We have this champion certificate. Okay, so now we will have another 5-minute talk by Director of Huawei Vancouver Research Center, Canada. Yeah, so let's welcome.
Yeah, hello everyone. Dear speakers and fellow researchers. So my name is Mingxue Wang, and I'm the director of the Huawei Vancouver Research Center. So I'm honored to stand here before you today to represent Huawei Technologies. So our company is proud to be a co-organizer of this event alongside other esteemed partners. So together, we have created an exceptional platform for global participants to showcase their technical prowess and advancements in the fields of the autonomous driving. So Huawei is a leading global provider of the ICT infrastructure and the smart devices. So we are committed to bringing digital to every person, home, and organization for a fully connected, intelligent world. So in the fields of the communication networks, IT, smart devices, cloud services, intelligent automotive solutions, and the digital power. So we provide customers with competitive, secure, and reliable products and solutions and services. So what people interact with experiences is our products. However, behind this leading products is a solid foundation of basic research and technological innovation. So our ongoing investment into exploration of mathematics, algorithms, chemistry, material science, physics, engineering, standards, and patents drive the competitiveness of our products. So heavy investment into R&D has and will continue to be one of the Huawei's key strategies. So Huawei reinvested at least 10% of the revenue into R&D each year. and over half of our workforce is dedicated to R&D. So by the end of the 2022, we had 114,000 R&D employees, accounting for 55.4% of our workforce. So the company has now has more than 80 foundational technology labs and over 170 joint and innovation labs around the world that will establish the AI research center for our mission of the lab is to make significant contribution to both the company and the society by innovating in artificial intelligence, data mining, and the related fields. So mainly driven by long-term and big impact projects. Research in the lab also tries to advance the state of the art in the fields of, as well as to harness the products and services of the company at each stage of the innovation process. As a world-class research lab, we are pushing the frontier of research and development in all areas that we work in. So we dare to address both the challenges and opportunities in the era of AI and big data to revolutionize the ways in which people think, work, and live, and the ways in which companies to do business through intelligentization of all processes with the slogan of from big data to deep knowledge. So research areas of the lab mainly include computer vision, natural language processing, search and recommendation, decision and reasoning, and AI theory. So founded in 2012, the lab has now grown to be a research organization with many significant achievements in both academia and industry. So by benchmarking industry thought on research and innovation, our AI academic impact has steadily increased year on year. So the amount of the papers accepted to the top conference is increasing. So the leading positions are achieved in more than 10 international competitions, including autonomous driving, visual and reinforcement learning. So autonomous driving is one of the major research and directions in NOAA's ARC lab. So with challenge problem as the traction, so we explore the frontier and make the breakthroughs of crucial components in autonomous driving, such as the perception, cognition, planning and control, simulation, and data mining. So all these innovations will continually support the technical competence and the success of our car business unit. So in addition to our technological expertise, so we value collaboration and knowledge sharing. So we actively engage with research institutions, industry partners, and academic communities to foster ecosystems of innovations. So NOAA's ARC Lab are located in 12 cities around the world. And it is connected to the world's leading innovation resources. By working together, we tackle the most challenging technical problems and propel the industry forward. So in conclusion, I would like to express our gratitude to the organizer or the partners for providing this remarkable platform. So we invite participants to join us in this exciting journey as we revolutionize transportation through autonomous driving technology. Together, let us create a safer, more efficient, and sustainable future for all. Thank you.
Hello everyone, this is E2EAD, and my name is Tom. In this presentation, we would like to introduce our solution for occupancy prediction challenge in CVPR23 autonomous driving workshop. The title of my presentation is Multitask Learning with Localization, Ambiguity, Suppression for Occupancy Prediction. The task is to predict occupancy state in specific level for it also increase price given multi-view images. Our baseline model we perceive body will consist of three main components: an image important to extract image features, a view transformer to transform 2D features into 3D features, and an occupancy important to produce occupancy predictions. We propose several improvements on the baseline. We propose very in-depth multi-class learning for task synergy and strong path to supervision signal for a level confidence. We propose localization ambiguity suppression for occupancy prediction refinement. We extend a short spatial period pooling to 3D tasks for better occupancy prediction results. We address data imbalance problem. And finally, we employ other techniques for performance improvement. Perspective semantic supervision is applied into image encoder. In particular, we use a private ambient feature level and build it into two ResNet blocks followed by a predictor. Since the image level semantic annotations are not available, we project 3D line point clouds with label into the image to get semantic annotation on the image, which is used to train the semantic branch. Moreover, via perspective semantic supervision, we provide each level component a short path to supervision signal, which help training deep network become easier. Occupancy prediction is dense prediction test which requires incorporation of large content. We extend a short spatial pivot pooling for 3D tasks to learn 3D feature with different sampling rate and field view. In addition, we propose localization and ambiguity suppression to define occupancy prediction. Unlike a system, the presence of object can be pre-defined by detected particles from 2D sensor. In camera system, we need to localize 2D objects from images. This leads to localization ambiguity in distant and small objects. We propose to suppress low confidence prediction using statistical prior. We also address the data imbalance problem. As shown in the figure, the portion of common classes is nearly 10,000 times higher than other rare classes. To address this problem, we employ weighted cross entropy and dice cost. We also employ other common techniques for performance improvements, such as high resolution input, long-term travel, test argumentation, pseudo labeling, and more. For our experiment, we use ResNet 15 as our baseline and training 24 ad hoc. We use 16 GPU I100 to train our model in about 3 days. Here are our experiment results. The baseline model achieved 33.5% MIOU. Here we show performance improvement. We added different components, including perspective semantic supervision, class balance loss, customized architecture, CVPR23, high resolution input, long-term temporal, pseudo labeling, test argumentation, localization ambiguity suppression, stronger backbone, and finally is model ensemble. Our final model achieved 52.45% MIOU on test split, and we win 7th place in the occupancy prediction challenge. This is the end of my presentation. More information is available on the technical report. Thank you.